All right, welcome to our first little bit of information on acids and bases. So today we're going to talk about the definition of what is an acid and what is a base. And then we're going to look at the pH scale and how we can use the pH scale in some calculations. So first off, we're going to go through some definitions. So Arrhenius acids and bases. An acid is basically something that produces a hydrogen ion, that's your first blank, or a hydronium ion, H3O+, when dissolved in water. So the general formula, you guys can write this part into your notes. You've got HA, so this is your acid. And if you dissolve it in water, what basically happens is the H that's on the acid goes on and attaches to the water molecule. So that H plus ion goes and attaches to the water molecule, making H3O+. And then what are you left with? Well, you're left with just A, which has a negative charge there. Okay. So H is a polar covalent molecule, HA, sorry, that contains a proton, which is H+, that easily dissociates and bonds with a water molecule. So remember, H+, if you go back to drawing your Bohr-Rutherford diagrams, if we draw my Bohr-Rutherford diagram for hydrogen, I've got one proton and no neutrons in the nucleus, and then I've got one energy level with one electron in it, right? So this is your electron. When I lose that electron and become positively charged, so if I lose this electron and it's gone, okay, now I've got basically just a positively charged ion, but basically all I've got left here is a proton. Okay, so that's why we say that H+, the symbol H+, is also the same as saying a proton, because when a hydrogen loses its one electron, the only thing that's left there is one proton. So here are some examples. You guys can copy this down into your notes. Hydrochloric acid. So when I take hydrochloric acid and it dissolves in water, basically you guys can write out the rest of the equation and then show me what happens to that proton, to that H+. So the H always goes and attaches onto the water molecule, making H3O+. And then you're left with Cl all by itself, and it has a negative charge to balance out the positive charge on the hydrogen. So same thing with HNO3 and H2SO4, okay? In HNO3, that hydrogen, again, is going to go and attach itself onto the water molecule. And I'm left with just NO3 minus at the end. And there is my hydronium ion. Sulfuric acid is a little bit different because I have two protons or two hydrogens in my molecule. So I'm going to take one hydrogen and another hydrogen, and they're both actually going to attach onto separate water molecules. So that's why I make two ions of H3O+. And then I'm left with my SO4 2- at the end. So what these are called here, these are basically called dissociation equations. And they're kind of important when we actually start to do some stoichiometry later on. Because as you can see, in my first two examples, my acid and my H3O+ ratio is 1:1, and again for HNO3, 1:1. But when I look at sulfuric acid, it ends up being a 1:2 ratio. So that's going to be important when we get to stoichiometry in the next video. All right, second definition is a base, okay? So a base is defined as anything that produces a hydroxide ion, OH-, when it's dissolved in water. So there are two different ways that this can happen. First is that the hydroxide ion dissociates from an ionic compound. So here, this M here stands for metal, so any metal, like sodium or calcium or beryllium, any of those bonded to a hydroxide ion will dissociate into the hydroxide ion and the positive metal ion that's left over. So two examples of those are sodium hydroxide and aluminum hydroxide. So basically all that's happening is that both of these molecules are breaking up into their ions, and when they do that, they're releasing hydroxide ions, okay? And that is your definition of a base, something that will make hydroxide ions when it dissociates. Notice again, when we're writing up the dissociation equations, they're important to know the ratio between your base that you start with and your hydroxide ions on your product side. So in the sodium hydroxide example, my ratio is 1:1. In the aluminum hydroxide example, my ratio is 1:3. So again, you don't really need to know that. I mean, you should be able to write out these equations and balance them out and make sure that they're all balanced. but this is going to become important in the next video when we use stoichiometry. The second way that bases can produce a hydroxide ion is when a covalent molecule steals a proton from a water molecule. So here is an example. So where I put B as sort of any covalent molecule. And if it actually steals this proton here from the water, well, what's the water left with? So if this is my H2O molecule, if I take away a hydrogen, what am I left with? I'm left with just OH with a negative charge. So that's how this guy here would make my OH and therefore be classified as a base. And then what are you left with? Well, the hydrogen attaches onto the B, and you have BH+. So here's a really good example, ammonia. So when you look at ammonia, ammonia is a base, but it doesn't have hydroxide in it. It doesn't have an OH in its formula. But it does make OH, and the way it makes OH, again, is by stealing a proton from a water molecule. So when I take ammonia and I dissolve it in water, it'll steal a proton and become NH4+, and then my water molecule is left over, the hydroxide ion is left over from my water molecule. All right, and I got a cute little comic here if you want to have a look at that. Put some more OH ions on it. We take our baseball, literally. Baseball. Okay, rough crowd. Oh, that's not for you guys. So, I'm not going to do those textbook questions now, but I am going to look at the pH scale really quickly, and then we're done this video. So, the pH scale, it's a measure of how acidic or basic a solution is. Okay, so you can fill that in, how acidic or how basic it is. The pH scale is a scale that ranges usually from 0 to 14, but this is not set in stone. You can have a pH of less than 0, or you can also have a pH of greater than 14. It just means it's extra acidic or extra basic. We usually say that the pH scale ranges from 0 to 14 because neutral is 7, which is right in the middle. So that's my next point there. If a solution is neither acidic or basic, it's said to be neutral. And neutral solutions have a pH of 7. So 7 is sort of halfway between 0 and 14. And there's lots of other reasons why the pH scale goes from 0 to 14. And if you're interested in those, take grade 12 chemistry. So that's what the pH is. Here's one little thing that's a little bit new for you guys. Water, even pure water, is not strictly just H2O molecules. It also contains some hydronium ions and some hydroxide ions. But those ions are at very low concentrations due to ionization. So here's what sort of happens, and this is a little bit of grade 12 chemistry for you, so you can kind of see where this is going. But what happens is if I've got two water molecules kind of hanging out together, one will steal a proton from the other water molecule, and that's how I make H3O+, and then this water molecule becomes OH-, okay? The only thing is these ions here, the hydronium ion and the hydroxide ion, are present in really low concentrations. In fact, the concentration is 1.0 times 10 to the negative 7th molar, which is, there we go, moles per liter. So that's a really small number of moles for every liter of water. But it does exist, and again, we'll kind of look at that a little bit more in grade 12 chemistry. So pH, or definition of pH, is also known as the power of hydronium ions. It's a measure of the H3O+ ions within a solution, and it's calculated as follows. So here is your formula for pH. So let's do a couple of examples with that. I'm going to skip over that. There we go. So, therefore, what is the pH of the solution with an H+ concentration of 1.0 times 10 to the 10? So, remember that pH is negative log times the concentration of hydronium ions. But chemists also kind of use hydronium and hydrogen ions interchangeably. So you could also write this equation like this, equals. Okay, hold on. Let me start that again so it's nice and clear for you guys. pH equals negative log of the H+ ion concentration. So, for number one, what is the pH of a solution with an H+ concentration of 1.0 times 10 to the negative 10? Remember that square brackets means concentration of whatever's inside the bracket. So if I have square brackets H+, it's the concentration of H plus ions. So in this case, this should be pretty straightforward for everybody to do. We use our pH equation. Oh, I'm not writing this very well today. Sorry. So we use pH equals the negative log of H plus. So if my H plus solution is 1.0 times 10 to the negative 10, then that's a negative log of 1.0 times 10 to the negative 10. If I punch that into my calculator, I get a pH of about 10.0. And hopefully you guys remember from previous years that something with a pH of greater than 7 is basic. Example number 2. What is the pH of a solution with an H plus concentration of 2.5 times 10 to the negative 4? Same formula. Negative. Oh, there we go. Equals the negative log of your H plus concentration again. So on your calculator, you punch in negative log of 2.5 times 10 to the negative 4. And when you do that, you should get 3.60. One thing to note, please make sure you're punching this in at the same at the same time as me to make sure you're getting the same answer. You're learning how to use that logarithmic button on your calculator. If you're not sure how to use that, make sure you ask me in class. Second thing, significant figures in pH. Because pH is an exponential or a logarithmic function, when we do sig figs, the number of sig figs in your final answer, this is going to be tricky to explain, or it's tricky to explain why, but just go with me on this. If there are 2 in the question, so I've got 2 sig figs in the question, my answer should have 2 decimal places, which it doesn't in my first one, so I'm going to fix that. So this should be 10.00. Okay, so the first 1 and the first 0 don't count, but the 2 places after the decimal are your significant figures. Okay, and for example number 2, that's why I put 3.60. Here I have 2 significant figures, so my answer has to have 2 decimal places. That's the rule. It's a little weird, and it doesn't really follow any of the other rules that we've done up to now, but that is the rule for sig figs. All right. Question number 3 is a little bit different. You actually need another formula to answer this question. So if you're taking math, you should be able to figure it out. But if not, I'm going to show it to you now. So what is the hydrogen ion concentration if the pH of a solution is 5.4? So here I gave you the pH, and I'm trying to get you to find the concentration. In order to do that, your concentration of H plus is going to equal 10 to the negative pH. Oops, pH. There we go. So to do this question here, so the concentration of your H plus ions is 10 to the negative 5.4. So when you plug that into your calculator, you get 4 times 10 to the negative 6. So again, I have 1 decimal place in my pH, so I only need 1 significant figure in my final answer. And then example number 4. This one I like to do because I'm showing you the difference between an acid with 1 H and an acid with more than 1 H. So I'm just going to divide up my screen in half. So if I have the pH of a 0.075 molar HCl solution, this is actually pretty easy. I'm going to actually punch in because of here. So if I write out my dissociation equation for HCl, it will make Cl minus and H3O plus. And everything is a 1-to-1 ratio. 1, 1, 1, and 1. So it's all balanced out. So that means that my concentration of my HCl here is going to equal my concentration of my H3O plus, okay? They're going to be equal because it's a 1-to-1 ratio. So when I plug it into my pH equation, it's a negative log of my H3O plus concentration. I can actually just punch in the number that's given to me in the question. Negative log of 0.075. And I get a pH of 1.12. Again, I've got 2 decimal places for the 2 significant figures. when I do my sulfuric acid, check this out. When H2SO4 dissociates in water, okay, I've got 2 hydrogens. So I'm actually going to make my sulfate ion, and then I'm going to make 2 hydronium ions, and I need 2 waters. So now not everything is a 1 to 1 to 1 to 1 ratio. I've got a 1 to 2 ratio. So that means for every 1 molecule of this that breaks up, I get 2 hydronium ions. So that means my concentration has to double. Okay, so if my concentration here is 0.075, then my concentration over here will be double that. So 0.150. So now if I punch that into my pH equation, negative log of 0.150, I actually get 0.24, I believe. So you can see that my pH of the exact same concentration of sulfuric acid is actually a lot more acidic than my concentration of my HCl, and that's because I have 2 hydrogens in every molecule. All right, really quick, just to end up, is the pOH value. So this is actually the power of hydroxide ions, and this is what we use in bases. So it's the measure of your concentration of your OH ions within a solution. So if you're dealing with a base, you can find the pOH of a base using negative log times the concentration of your, negative log of the concentration of your hydroxide ions. If you ever add up a pH and a pOH of the same solution, they should equal 14. So let's do one quick example. You've got your 2 new sort of equations there. So the pOH of a solution with a concentration, hydroxide concentration of 1.8 times 10 to the negative 4. You're going to use pOH, because it's the power of hydroxide ions, is the negative log of your OH minus concentration. So that's pretty easy. We punch in our numbers, 1.8 times 10 to the negative 4. And we're going to get a pOH value of 3.74. And then my last example is find the pH and the pOH of a 0.0050 molar NaOH solution. So again, in this case, I can find my pOH really easily because I have hydroxides in my formula. So that's the negative log 0.0050. So in the end, my pOH would be 2.30. And then pH plus pOH equals 14. I know my pOH, so this will be pH plus 2.30 equals 14. So I can rearrange my equation and get that my pH is 11.7, which is greater than 7, so that's basic. And that makes sense because I have sodium hydroxide as my compound, which is a base. So that's it for acids and bases and pH calculations. We'll see you in class to clear up any misconceptions you have.